All right, welcome to Unit 10, Organic Chemistry Notes. Organic chemistry is completely based on carbons that contain carbon. Now, the nice thing about carbon is that all carbon have 4 valence electrons. We see those here. And they're all going to look to form 4 covalent bonds. That makes carbon a really good central building block. Another common atom you're going to see in organic compounds is hydrogen. Now recall that hydrogen has only 1 valence electron and is only going to form 1 covalent bond. Organic compounds are based on the number of carbon atoms that they contain. So when we're naming them, we have to know these prefixes. 1 carbon, meth, meth for 1. 2, eth, eth for 2 carbons. 3, the prefix is prop. 4, bute. 5, pent. 6, hex. 7, hept. 8, oct. 9, none. And 10, the prefix is dec. It is very important that you memorize these structures. You're going to hear these terms and see these terms a lot. Alkanes, the most basic of hydrocarbons. So alkanes have only single bonds between their carbon atoms. Alkanes are also called saturated, which means they're full of hydrogen. Saturated means full. They have the maximum number of hydrogens on their carbon chain. And the general formula is CnH2n plus 2. But I wouldn't spend much time worrying about that. That does not come up very often. When naming alkanes, they always end in the suffix ane. Let's take a look. Remember those prefixes from the previous page? Well, when we have 1 carbon, the prefix is meth. And the ending is ane, letting us know that they're all single bonds. When we draw the structure, I always like to start with the number of carbons. So again, the meth part tells us that we have 1 carbon. Now we also know that every carbon is going to make 4 bonds. So there's my 4 bonds. Since I only have 1 carbon, I want to now fill up the rest of those bonds, those empty bonds, with hydrogens. So there we go. And again, looking back at the general formula, CnH2n plus 2. Well, in this case, we have 1 C, so our N number is 1. We have H's, we have 2 times 1 plus 2. So 2 plus 2 is 4. There are our 4 H's. Moving on to 2 carbons. Again, the prefix for 2 is eth, and again, the ane tells us that they are all single bond. When drawing this, I would start with my 2 carbons, eth, 2. Again, every carbon has to have 4 bonds, so I draw those bonds around my carbon. Remember, there's 1 bond connecting the carbon, so each carbon is now only going to have 3 empty bonds. I then fill in those empty bonds with H's, and there's my structure, ethane. 3 is prop. Again, ane, telling us they're all single bonds. I would start with my 3 carbons. There they are. There's my chain of 3. 1, 2, 3. Each carbon has 4 bonds coming off of it, so I'd make sure I draw those empty bonds, and now add my H's to fill up all of those empty bonds. C3, H, 2 times 3 plus 2. 2 times 3 is 6, plus 2 is 8. There's 8 hydrogens on that structure. 4 carbons, bute, not but, ane telling us they're all single bonds. So again, I'm going to draw my chain of 4 carbons. Bute tells me there are 4 carbons. Make sure each carbon has 4 bonds and add your H's around the outside. 5 carbons would be pent. Again, there's my 5 carbon chain. Each carbon makes 4 bonds. Make sure that each of those bonds is attached to a hydrogen. And there we go. 6 carbons. Again, the prefix for 6 is hex. The ANE tells us they are all single bonds. Fill up each of those single bonds with a hydrogen, and there's our structure for hexane. The prefix for 7 was hept. ANE at the end tells us they're all single bonds. So there's our 7 carbon chain. Fill it up with hydrogens. There is heptane. Octane. I kind of ran out of room, but it also provides me a way to show you what's called the condensed structure. Generally, I don't want you guys drawing this. I want you drawing your structure and showing me all the bonds. But you might sometimes see the condensed structure written on a test question or homework question. And what we have is our 8 carbons, C, 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 and C. These are 8 carbons. The 2 on the end, so here's the one on the right end and the one on the left end, have 3 carbons each. If we look back at heptane, we can see the carbons on the end of the chain have 3 hydrogens each. So CH3 and CH3 on the end, and then we have CH2s in the middle. Again, all of our middle carbons are bonded to 2 hydrogens. So CH2, 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 and CH2. 8 total oxygens, 8 total carbons, all of them filled up with hydrogens. There's a saturated alkane. 9 carbons would be nonane. This is super condensed structure, and you will never be drawing this. I will not give you credit for this in a homework or test. But in case you ever see it, we have the 2 carbons on the end that have the CH3 and the CH3, and then in between them we have 7 repeating CH2s. So 2 on the end plus 7 in the middle, 9 carbons, there's nonane. And finally, decane, 10 carbons, all single bonds. There's a very long decane chain. So that's naming for alkanes. Cyclic hydrocarbons. As the word cyclic kind of sounds like, it's a circle. It's a ring of carbons. The general formula is CnH2n. Basically the same as the alkane, but we don't have those 2 extra hydrogens on the end. Instead of having those 2 hydrogens on the end, the carbons are connected to each other in a circle. Naming cycloalkanes is really pretty easy. You just count the number of carbons like we did before, use the prefix, and put cyclo in front. So here's an example. We have 1, 2, 3, 4 carbons. 4 carbons in a ring. 4 carbons would be bute. They're all single bonds. The ending is ane. We put cyclo in front, and we come up with cyclobutane. In another example, we have 1, 2, 3, 4, 5, 6, 7 carbons. We have to think about what that prefix is. 777. That's hept. There's a circle. They're in a circle, a ring. They're all single bonds. So cycloheptane. That's how you name cyclic hydrocarbons. Alkenes. So notice the difference. Alkanes ended in A-N-E. Alkenes end with an E-N-E. Alkenes are hydrocarbons that contain at least 1 double bond. When naming alkenes, we end with the suffix E-N-E. The general formula is CnH2n. It's the same formula as cyclic alkanes, we have 2 fewer hydrogens because of that double bond. So here's an example. 2 carbons, 1, 2. We have that double bond. We think about our prefix for 2 carbons, that's F. It's got a double bond, so we put an ending of ENE. And there we have ethene. Again, the prefix eth tells us there's 2. ENE tells us there's a double bond. Next up, we have alkynes. Again, notice the ending. It's a YNE instead of an ENE for alkenes or an ANE for alkanes. Alkynes will be hydrocarbons that contain at least 1 triple bond. As you might have guessed, the ending for alkynes will always end in YNE. The general formula is CnH2n minus 2. Again, here's our example. Just like every other example we've done, we count the number of carbons, 1, 2. We know the prefix for 2 carbons is eth. It's got a triple bond, 1, 2, 3. So we end with YNE. This is ethyne. Ethyne. The common name of ethyne is acetylene. It's a commonly used ingredient in welding torches, the gas that they burn in welding torches. Another example, there's our triple bond, 1, 2, 3. We count the number of carbons, 1, 2, 3. We think about the prefix for 3 carbons, prop. Because of that triple bond, we add the ending YNE, and we have propyne. Saturated versus unsaturated. These are common chemistry terms you'll hear quite often. In fact, you should have heard it last year in biology. As I mentioned a couple slides ago, a saturated hydrocarbon contains the maximum number of hydrogen atoms. All the carbons are only single bonded to each other, which means all the other bonds that they have to form go to hydrogens. An unsaturated hydrocarbon does not have the maximum number. It is not full or unfull. That usually means it contains at least 1 double or triple bond. So here's an example of a saturated alkane. Again, notice we have the maximum number of hydrogens around that carbon chain. Here's an unsaturated chain. Notice there are 2 fewer hydrogens because of that double bond. Those carbons are bonded to each other redundantly and therefore are not bonded to the maximum number of hydrogens. This is really, really important in biology and as far as your health goes as well too. Saturated fatty acid chains, here's a picture, tend to be long and straight, whereas unsaturated fatty acid chains, although they may be equally long, tend to be bent, or sometimes we call this a kink, due to that double bond. The bond angle is a little bit greater, the kink goes outwards, and that's a pretty important fact in biology. Again, here's a picture of a cell membrane. Notice those kinked tails. That prevents the membrane from being too packed. It allows it to be a little bit more fluid instead of tough and strong and unflexible. This way, as your cells or all cells float around, they can bump into things like a water balloon, and that cell wall can bend a little bit without breaking. If all of your fatty acid tails were saturated, they would be straight, they would pack way too tightly, and if they were poked, if they ran into something, they would probably burst, like when you really hammer a water balloon and poke it too hard. But again, imagine a water balloon and you kind of poke it, it goes in a little bit, it can move in, it can move out. That membrane doesn't break so easily. That's really important. You've probably also heard of saturated and unsaturated fats. And they'll tell you, doctors will, that unsaturated fatty acids are a lot healthier for you to eat. The reason this is is that because of that kink, because of that kick, unsaturated fatty acids are not as dense. Again, we can see that picture here. There's a lot fewer of those fatty acids because those tails need a little bit more room because of that bend, because of that kink. So unsaturated fatty acids tend to be vegetable oil. They're liquids, they're not as dense, versus saturated fatty acids are usually more along the lines of butter. Think about a stick of butter and how solid that is because of the density that those saturated fatty acids take. Numbering alkenes and alkynes. Once we get a longer hydrocarbon chain, generally longer than propene or propyne, we have to use numbers to signify the location of the double or triple bond. So for instance, let's look at the difference between 1 butene and 2 butene. And but tells us that there are 4 carbons, 1, 2, 3, 4. The ENE tells us there's at least 1 double bond. The one out in front lets us know that that double bond is on the first carbon. So there it is. Versus 2 butene. Again, but, there's going to be 4 carbons. ENE tells us there's at least 1 double bond. The 2 out in front lets us know that that double bond is on the second carbon. So as we count 1, 2, there's the double bond. The 2 signifies that that double bond starts on the second carbon. Over here, the double bond started on the first carbon. Why do you think hydrocarbons only larger than propene and propyne need the numbering system? Well, if you think back to eth, that's 2 carbons, ethene and ethyne, there's only 2 carbons. So the only place a double or triple bond could be is between those 2 carbons. Similarly, with only a 3-carbon chain, if you could turn the structure left, right, up, down, front, and center, the double or triple bond would always have to be on the first carbon. So it's redundant to say 1 propene. It has to be 1 protein. There is no 2 propene or propyne. Counting carbons. Alright, when you're counting your carbons and numbering your double and triple bonds, you always have to use the lowest possible number. So here we have an example. Notice the double bond in the middle of the structure. If we were to count from left to right, we would have 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. And we would call this 3-pentene. Again, the pent telling us that there are 5 total carbons, the ENE telling us that there is a double bond, the 3 telling us that that double bond starts on the 3rd carbon. But this is not right. There's no rule that says we have to count from left to right and not right to left. If we count the other direction, right to left, now the double bond is on the 2nd carbon. Because 2 is lower than 3, the rule is the lowest possible number must be used. So this structure is correctly called 2-pentene, not 3-pentene. When you're working with a cyclic alkene, if there's only 1 double bond, you don't have to number it. But it would mean that your numbering system starts on that first double bond. So for example, we would start with a 1 here, and that would be your 2nd carbon there. 1, 2, that double bond dictates where we start counting for our structure. 6 total carbons. There's a double bond, so we put E and E. It's in a circle, so we call it cyclo.